Hello friends, after discussing the Nyquist criteria for distortionless transmission, we talk about equalization process. In the baseband transmission of digital data, there is a requirement of Nyquist channel, that is a type of band limited channel, and it is a linear type, for example telephone channel. In order to get high speed transmission of digital data, this linear band limited channel is not directly used, and the more efficient and appropriate approach is the combining effect of two basic signal processing operations. First is discrete PAM and second operation is linear modulation scheme. In discrete PAM operation, the amplitudes of the successive pulses in periodic pulse train is encoded into a discrete sets of possible amplitude levels according to the M-array line encoding technique. After encoding, a linear modulation scheme is introduced that is based on bandwidth conservation scheme and transmit the discrete PAM signal over the telephone channel. This combining effect introduces a high-speed digital data transmission, that is a type of baseband transmission. But in practice, the problem arises in the physical implementation of pulse shaping filter PT, which is simply the double convolution of impulse function GT, ST and QT corresponding to transmit filter, channel and receiver filter respectively. And this pulse shaping filter PT always results some residual distortion for intersymbol interference, and this becomes a limiting factor for data rate and affect the transmission speed of digital data. And in order to compensate this residual distortion, that is a type of intrinsic distortion, a process of equalization is performed. And for equalization process, an equalizer filter is used, having delay line, adjustable weights and summer as a building blocks. Here the delay line consists of a taps that are uniformly spaced at every capital T second, that is called symbol duration. Here T is called delay time. At every taps of the delay line, there is a connection of adjustable weights denoted by W. And at last, the delay and weighted version of input signal is added successively using summer at the output side of the equalizer. The combination of delay line, adjustable weight and summer called the linear equalizer or simply called tapped delay line equalizer. Here, to consider a symmetry, we design a delay line with 2n plus 1 tap points. Here, each tap is connected with adjustable weights with values W minus n plus 1 up to W0 and then W1, W2 up to Wn minus 1, Wn. After this, the delayed and weighted version of input signal get added using summer and we get equalized output signal denoted by y function nt. And due to this feature, this equalizer is called transversal filter and taking a part as a receiver. This transversal filter performs both pulse shaping as well as residual distortion equalization and hence called transversal filter. Now, using this combining feature of transversal filter, a zero forcing equalization is performed that we are going to discuss. In zero forcing equalization, we consider impulse response CT, which corresponds to the combined characteristic of both transmitter and channel. At the receiver side, we use adjustable transversal equalizer, that is the type of tap delay line filter and is denoted by equalized impulse response HT. Here 2n+1 number of taps are considered on the basis of symmetry and corresponding weights value are W-n to Wn. Here the input binary sequence AK is applied to the input block CT, and at the output of the transversal filter we get an equalized signal YT. So for zero forcing equalization we consider a cascade system, and the overall impulse response of this cascaded system is the convolution of CT and HT, denoted by PT, that is called pulse shaping function. Also for transversal filter at the receiver we consider structure symmetry, and it is equivalent to summation Wk del T minus Kt, taking limit k equals to -n to +n, where del T is called impulse function and here del T minus Kt is called periodic impulse train. Also Wk is the weight connected to kth tap of delay line equalizer. So in place of Ht, that is called equalized impulse response, we can write summation Wk del T minus Kt. After this, we consider a linear cascaded system. For this, we take a linear convolution of two functions, that is Ct and del T minus Kt. After the linear convolution and using the property of impulse function, that is Ct convolution del T minus Kt, we get Ct minus Kt. So the overall impulse response in terms of pulse shaping function Pt is equals to summation Wkc T minus Kt, taking limit k equals to -n to +n. And after performing convolution, we take sampling at t equals to I capital T, where capital T is symbol duration, and Pt get converted into sampled pulse T function It, that is equals to summation Wkc within bracket I minus k into T. And for our simplicity, we can write this expression in compact form, denoted by Pi equals to summation Wk C suffix I minus k, taking limit k equals to -n to +n. Now, in order to get zero intersymbol interference, the value of Pi must be equals to 1 for I equals to 0 and 0 for I not equals to 0. And this requirement is fulfilled after equalization at the receiver side. For this, at I equals to 0, the value of summation Wkc I minus k is equals to 1, and at I equals to ±1, ±2 up to ±n, the value of summation must be equal to 0. And this adjustment make an optimum equalization that minimizes the peak distortion and corresponding intersymbol interference. So, in equalization process, we can adjust the weight value, and which results zero intersymbol interference. Now, we note a point. In the equalization process, as the value of n tends to infinity, then our equalizer filter approaches an ideal condition and satisfy the ideal solution of Nyquist criteria for distortionless transmission. So in equalization process at the receiver side, the value of adjustable weight must be large. But when we consider large value of adjustable weights, it will increase the cost of equalizer at the receiver side. So in order to get optimum output, we must take care of adjustable weight and costing of the cascaded system.